Start recording. And we're going to start talking about forces. I think we've given people enough time to get in. I want to make sure we have enough time to get to the FRQ. So let's talk about forces. So the first thing I'm going to do is talk about the difference and the similarity between inertial masses versus gravitational masses. So inertial mass is just a measure of inertia, which is, resistance to acceleration. Whereas a gravitational mass determines the force of gravity, determines Fg, or weight. But here's the big key. Experimentally, sorry about my spelling. Experimentally, they are equivalent. There has never been a time that they have been shown to be different, but College Board still likes you to know that they are slightly different from one another. Because in this case, Fg equals mg. This is the gravitational mass, but if we're doing net force equals ma, this is the inertial mass. And I'll talk more about that when I get to the laws. Okay, so Newton's first law, which is the one that I think you guys were the most familiar with. An object at rest stays at rest, and rewriting slightly, and an object in motion has constant velocity unless acted on by an external net force. And this is just because objects with mass have inertia. So they want to keep doing what they're doing. And that's really, Newton's first law. Sometimes they'll ask about it, understanding that this is a net force, an object, and understanding that that in motion, an object in motion will stay in motion really means that the object is going to have constant velocity unless a net force acts on it. So that's the first law. The second law is one we use a lot, is F net equals ma. It's sometimes written as sum of the forces equals ma. And on the equation sheet, it's rearranged to be A equals the sum of the forces divided by m. But really all that means is acceleration is directly proportional to the net forces, and it is inversely proportional to the mass, because the mass, again, this inertial mass resists acceleration. Big objects are harder to accelerate than smaller objects. And then I think that's all I want to say about Newton's second law. Newton's third law is, the action reaction pairs, where if we have two objects, a hand, this is going to be a really great hand, pushing on a wall or any other object, the force on the hand by the wall is going to be equal to the force on the wall by the hand. The force on one object by the other is going to be equal to the equal and opposite of one on the other. Okay? So that's Newton's third law. Every action force has an equal and opposite reaction force. In words, that's Newton's third law. Do you have any questions thus far? We're feeling okay. Probably okay. Okay. A couple of other reminders about forces. Force of gravity. Fg equals mg. This is on Earth, and Fg equals big G m1 m2 over r squared. I will review this in more detail again at a later review, but I just want to remind you. This is on Earth. This is everywhere. This one's easier to use. If you can use it on Earth, please do. And then normal force, Fn, is always perpendicular to a surface. Yeah. And yeah, I think that's totally fine. Another good thing. And I'm going to do a few things on friction. So remember, friction, it's actually written on your equation sheet as like this times normal force. And this is just, they're being a little bit mean here, but really all it means is a friction force is going to be, up to some, it's going to be, proportional to the normal force, and it's going to be some value up towards some maximum frictional force until you overcome it. But there's also static friction and kinetic friction. Static is, getting things going. You need to overcome it. whereas kinetic friction is when things move. So a couple things to know about that. The force of static friction, which is going to be SF, is going to be greater than the force of kinetic friction because it's harder to get something moving than it is to keep it moving. Also, yeah, because of this, the force of static friction is going to, equal mu static friction times normal force. The coefficient of friction, don't forget this is called the coefficient of friction, which is just, it's unitless, and it depends on roughness of a surface. So like, U sandpaper is going to be greater than U ice. That's where the actual material property comes into play here. Mu rubber would be, between the two here. Okay. I think that's all I want to know. This is, for the 4 objects are sliding. You know what, I'm going to add the other thing, and it is always parallel to an object's motion. Okay. And that's the big things that I want you to know about friction. I guess maybe one, I keep saying that's the last thing. It is independent. I'll write this right here. Force of friction is independent of surface area. We didn't hit that super hard this year, but it's good to know that it's independent of surface area, meaning that if it's a small amount for an object, in contact with a surface, or a large amount that, of an area, in contact with the surface, then it's not going to change the force of friction. It might mean a difference in force of friction per unit area, but it is not going to change the overall force of friction experience between two objects. Okay. Do I have any other questions on this stuff? Okay, let me see here. Any chat question? Okay. Anywhere with a constant gravitational acceleration? Yeah, I'd say that's fine. Sorry, I moved on from that. But yes, as long as you have a constant gravitational acceleration, that is totally fine. But you need to know the G, the gravitational field strength of that area, and you need to be very close to that area. As you move far enough away, it will no longer be fine to use this unless you are taking into account the variable equation, G equals G m over r squared, where you're taking it into account. Does that answer your question, John? maybe. Did you hear my question, John? Okay, cool. Good. All right. Sorry about moving on from that, missing it. Okay, last thing I'm going to say, remind you before I'm going to talk about actual, Flatwood and Atwood machines. If an object is stationary, so stationary or constant velocity objects, then F net is going to equal 0 because F net equals MA, and if this is 0 meters per second squared, then F net equals 0 newtons. All balances or all forces are balanced if you have a constant velocity or things are stationary, and that includes objects moving. If this was like an object that is at terminal velocity, going as fast as it possibly can, because then the force of drag, like of air resistance, I'll just call it air resistance, equals the force of gravity, and as such, terminal velocity is a constant velocity. Okay. I think the only other thing before I get into the Atwood machines that I just thought of are if you have an object sitting on a surface, let's say a stationary box on the surface. So if you were asked to draw the free body diagram for this box, stationary on a slanted surface, what you should do is you should draw FG, you should draw the normal force, and then you should draw the force of friction. So this is, usually they say no components, do not draw components, but it's just a good practice. If they just ask you to draw a free body diagram, this is how you should do it. But if you wanted to solve for what the free body diagram is, solve for force of friction, solve for the normal force, something like that, then what you should do is draw these two forces, and then I'll remind you to break your force of gravity into its components. FGX and FGY, because we have bent, we have rotated the axes. So FGX and FGY should look like this. And then, equation wise, you would get sum of the forces in the x direction is F force of friction minus, or I guess I'll call it a negative force of friction. We'll call this positive. Negative force of friction plus FGX, and that equals 0. And then in the y direction, we have normal force plus a negative FGY, which would also equal 0. And then actually, a little bit of a simplification. If you wanted to solve for this, you knew this angle theta. then I'll remind you it is the same angle as this theta. And so FGX, because FGX is the opposite side of this angle, is going to be sine of theta times FG, because this is the adjacent side to the angle. FGY is going to be cosine of theta times FG. Okay. Any questions before I move on to Atwood and Flatwood machines?
Yeah, what is terminal velocity again?
Great question. So I didn't hit it too hard, but it's like for an object in free fall that experiences air resistance. So oftentimes we just say you can ignore air resistance, but if you can't ignore air resistance, then terminal velocity, then that says then terminal velocity is the maximum velocity you can, or the object can experience, because if air resistance equals Fg, so you get a constant velocity. Faster things have more air resistance. So there is a point at which if something is falling, eventually it's going to be moving fast enough that its air resistance equals its force of gravity. Does that make sense? I didn't hit it hard, but it's just a little thing that you can know. Okay. Any other questions? No problem. Okay. So if no other questions, then I'm going to talk about Atwood and Flatwood. And they usually draw it, and sometimes people don't call this a Flatwood machine, but I just think the general idea, you have two objects. This is M1, this is M2. This would be, a traditional Atwood machine. What I call a Flatwood machine is some variation of this, where we'll call this M3 and M4, just to differentiate between the two. Where you can solve, they'll oftentimes ask you to, solve for acceleration or tension or both. So the first thing you do, and if you were asked to solve for the tension or you were asked to solve for the acceleration, solve for this first. And the secret to solving for this is to bend your axis around a pulley. So this is going to be a pulley. This is going to be a pulley. It is oftentimes called massless. or a negligible mass, something like that, where meaning you don't really have to take it into account other than the fact that it is going to allow the direction to change. So with this, mass 2 is greater than mass 1. So it is going to, the whole system, sorry about the zooming issues. The whole system is going to accelerate in this direction. So we're going to call it positive, whichever direction it is going to move, we're going to call that positive. We can call this X, we can call that whatever you want to. It doesn't really matter what direction you call it, as long as you keep this all consistent. So to figure out the forces, you would solve for the net forces, and that is going to equal the mass of the whole system times the acceleration of the system. That's how you would figure out what the acceleration is. So in this case, on object 2, M2, I guess I'll start with M1. You have the force of gravity. So on M1, there is the force of gravity. And you have the force of tension. And then on M2, you have FG2. I'll call this FG1 and this FG2. You have the force of tension, and you have a bigger, sorry, FG2. It's got to be bigger than this for you to get an acceleration. So on object M1 in our system, we have FG1. It's in the negative direction because it's opposite the motion, plus the force of tension. On M2, you have a negative force of tension plus FG2, which is going to equal the mass of the system times the acceleration. These two are equal and opposite. We're going to have equal tensions on both sides as long as this is massless. So we don't have to worry about them. And so you get negative FG1 plus FG2 equals the mass of the system, which is both masses together. Both masses contribute to the mass of the system times the acceleration. So that's what you would do first. And then you divide by M1 plus M2, M1 plus M2. And that's going to give you your acceleration. Okay, then once you have that acceleration, you can solve for the tension on one of them. You just now isolate one of the systems. And then you can say, the FT, or sorry, the sum of the forces on, we'll just say M2. Some of the forces are going to be, FT, negative FT plus FG2, which then equals just the mass of this new system times the acceleration of the system, which you have already solved for. So you should know your M2. You should know your this, because it's just going to be M2G, and then you can solve for this. I'm not going to spend all the time solving it because I want to get to a Flatwood. Do you have any questions on that before I talk about Flatwood? Okay. If I don't have any questions, if we have this scenario now, and I draw my forces, we're going to have a normal force, a force of gravity, and a force of tension acting on M3. And we're going to have a force of tension and a force of gravity acting on this one too. So if this is the case, force of tension, and we, combine all the system together, and we want to figure out the acceleration, we're going to have the sum of the forces, again, for the whole system is going to be Ft. The whole system is going to move this way, right? Ft plus a negative Ft plus Fg4 equals the mass of the system times the acceleration. These are going to cancel again, and you're going to get Fg4 equals the mass of the system times A. Then you'd solve it just like you do over here. Note, this is only true if this is on a frictionless table or something. This word table. Okay? And then you could use this in order to solve for the tension just like I did over here. But some things to take note. If this is really, really massive relative to this, then this is not going to be enough force because, if the mass of the system gets very, very large, if I solve for A here, Fg4 over mass of the system, mass of the system, mass of the system. If you think about this, if this is really, really big and this is hardly providing any mass at all for a force of gravity, then this will be really big and we will have a small acceleration or none if it's really, really big. If the opposite is true, if we have a mass here that is very, very large, that's going to make this really, really large. Let's say it's 100 times greater here than this mass here, then there's going to be very little mass relative to the system. Almost all of it will be in here. So then you'll get a very large acceleration that'll get pretty close to G, right? Because it'll be, if this is just left to fall, this is really, really, really big and this is really, really, really small, it's going to be almost like in free fall. And that may be where I leave this. Do you have any questions on this? I already talked more than I wanted to talk before I get you guys practicing. Okay, so I'm going to stop recording